Welcome everyone. Today I would like to present the search for boosted Higgs boson decaying into bottom quark pairs in CMS using full LC run-to data. Before I start, I would like to put this search into a broader perspectives of CMS boosted searches. CMS has been pushing technologies for understanding boosted objects that help us to explore different new phase spaces. In the context of digest resonance searches, the boosted searches has enabled us to explore the low mass and small coupling regime, which was not accessible with the classic digest searches due to trigger limitations. For Higgs physics, the same techniques enables us to probe the PT range that is difficult for other channels due to their smaller branching ratios. You can see the Higgs CC and Higgs gamma gamma is really running our statistic here. And this highly boosted regime is also where new physics contribution could become sizable due to the larger momentum transfer involved in the scattering. So where do we look for a boosted Higgs boson? To access the highest possible momentum, we really need to catch all the Higgses. And so the natural choice would be the Gruen-Gruen fusion production plus the BB bar decay, which was once thought to be impossible at the LHC due to the overwhelming QCD dijet background that is 6 orders of magnitude larger in cross-section. In the following, I will highlight the techniques we used in this search to overcome this hurdle in the highly boosted regime. So there are really three main ingredients to bring the signal to background ratio to a manageable level, about 1%. Namely, the kinematic requirements at the trigger level, jet substructure to select large radius jet that has a two-prong substructure inside, and of course B tagging to select the B jets coming from the Higgs decay. So let's go over each one of them in more details. At the trigger level, the goal is to keep the PT threshold as low as possible while maintaining a manageable trigger rate. CMS has implemented To do this, CMS implemented high-level trigger paths that trigger on high PT aka jets or large HT events with a sizable tree mass in the leading jet. Having this tree mass requirement is the key to keep the rate down, and that brings us the first factor of 10 in the signal to background ratio. This is also what sets the momentum scale of the analysis as we select the phase space where the triggers are almost fully efficient, which is PT greater than 450 GeV and a soft dry mass of greater than 40 GeV. Another factor of 10 comes from the jet substructure. We're using the N2 variable, which is the ratio of the 3-point to 2-point energy correlation functions within the groomed jets. Jet substructure are, however, in general, highly correlated with jet mass. So a cut on N2 could reduce the QCD background, but also significantly sculpt the mass spectrum like so. Therefore, we employ the DTD technique where we compute the N2 contour at a fixed efficiency as a function of jet mass and PT from simulations, and then subtract this contour from the N2 computed from the raw N2. By design, cutting on this N2 DTD variable would give a constant efficiency as a function of mass. So after the correlation, the sculpting is gone. Another 2 orders of magnitude comes from the double B tagging, which tries to identify 2 B hadron decays within a single large radius jet. Compared to the first boosted Higgs to BB search, we upgraded the BDT based tagger to a DNN1. With the more complex model architecture, we also give more low-level inputs to the DNN model, including up to 60 checks and 5 secondary vertices that help us to gain about 50% more signals at the same mistake rate. However, with greater discrimination power comes greater mass sculpting as well. There are residual mass correlation even after trying to mitigate it with the penalty terms in the loss function during trainings. So after the correlation, there's still residual sculpting. This makes using the more powerful decaying analysis, also more complicated. To combat this, we adopt a similar approach with the decorrelation in N2, where we build the expected mass sculpting map using simulation and apply the data to Monte Carlo correction to account for the residual differences. Visually, this is how each component of the sculpting is done. You can see the Monte Carlo map really captures most of the expected sculpting with the correct overall efficiency of 1%. Therefore, the data to Monte Carlo correction is of the order 1 and reasonably flat against mass and PT. And this is the resulting mass sculpting map. So an important step to validate this background estimation method is to measure the C signal strength. You can see with the improved deep double B tagger, the C peak becomes very prominent even in a single PT bin, whereas it was much smaller before. With such a bright standard model candle, the measured C signal strength is consistent with the standard model expectation and is also consistent with 1 across all PT bins. Then we move on to extract the Higgs signal strength, which is found to be 3.7 with roughly 41% uncertainty. This analysis is still statistically limited, with one of the leading sources of uncertainty coming from the ones related to the modeling of the mass sculpting shapes. This signal strength corresponds to an observed significance of 2.5 sigma, where the expected one is 0.7 sigma. So after seeing these small excess, we are interested in whether this excess comes from a particular PT bin. So we compute this signal strength as a function in each of the PT bins. And we found an increasing trend of Higgs signal strength as a function of PT. This is reminiscent of how new physics could enhance the Higgs PT cross-section spectrum. To facilitate the theoretical interpretation of this trend, we unfolded the detector reconstruction effects and compared the fiducial cross-sections with the latest Gruen fusion predictions. That also includes the latest finite top mass correction, which was very difficult to obtain. From the unfolded spectrum, the excess beyond 650 GeV has a local significance of 2.6 sigma with respect to the standard model expectation. Although the central value really follows a nice trend, you can note that the uncertainty remains quite large in the highest PT bins. To summarize, this analysis utilized some of the tools that has been built from the Boost community, namely the jet substructure, deep neural taggers, and the corresponding decorrelation techniques, to enable us to see some of the really rarest Higgs events produced at the highest momentum. We are probing at a region where it's less than 1% of the inclusive cross-section and the momentum scale greater than 1 TeV. We have seen some exciting signs in the boosted regime with this analysis, and there is still plenty of room to explore in this regime, say, for example, in other decay channels and protection modes. And we look forward to have more analysis to come. Lastly, I would like to end the presentation with an event display of an Higgs event candidate produced with some of the highest transfer momentum. Thank you.